So we've imported a valve geometry as parts. You can see them here populated in the parts tree. And what I'd like to do is rotate the position of this single component. So the first step in doing that is we need to figure out what coordinate system to rotate a valve. So we can check our imported coordinate system, and we'll see that it actually does not lie directly in the center of the valve. So what I'm going to do is change my projective mode to parallel so I can more easily see this circle, and I'm going to create a new coordinate system along the axis of this valve. So let me hide this. We can see how we have a nice circle here to select, and I will turn on the mesh so I can see my node points. Right click on coordinate systems, new, Cartesian or cylindrical depending on what you'd like to do. I'm going to select 3 points on an arc in order to define my coordinate system. And so now we have the coordinate system down the axis of this valve. So I can bring back my valve geometry, and now we can rotate it. So let's start out with a full open or full closed position. I'll go to transform, rotate. Let's go 45 degrees about the z-axis of our laboratory Cartesian 1 coordinate system. You can see here we're full closed, and now we're full open. So let's start with this piece of geometry. So the next step, after I get my valve in the position I'd like it, I need to cap the inlet and outlet in order to establish my internal flow domain. So what I'm going to do is open up the geometry inside of our repair tool so that way I can fill holes. And during this initial check, I never really check the bottom 3 here. These are more topological problems with a remeshed surface, less problems with a imported surface. So what I need to do is allow the selection of edges and create a new boundary, and we'll call this inlet. And I'll double click here and hit H on my keyboard to hole fill, and then I will add those triangles to this boundary that I created. Do the same thing over here. Create a new one called outlet. Okay. Edges, H for a hole fill, modify. Alright, now we've capped both of those. You could continue on if you needed to do a conjugate heat transfer problem, and you could actually merge imprint the valve onto the housing and continue to do it that way. But in my particular case, I just want the internal flow passage. So now you can see under geometry I have inlet and outlet. So let's send this to the CFD world. Now we keep parts and regions separate so that you can have a different geometric definition from your CFD definition. So now when I send all these geometric parts to regions, they now get mesh conditions, they now get physics conditions. But if I go up and change any one of them, the physics and mesh conditions simply reference the geometry. And that way, you can essentially quickly do modifications to geometric definitions. So now what I'm going to do is create one region for all parts because I want one internal fluid region. I want one boundary per surface so that I get all of my boundaries that I've created, and I don't have any contacts, so it doesn't really matter whether I have this checked or not. So I have my inlet, my outlet, and my 2 other components. So next step is to define our mesh. So the biggest question always is, well, how am I supposed to attack this geometry? How am I supposed to know what I need to do here? Well, the first thing to look at is the repair tools. So we can go back up to our parts and we can take a look. And I'm going to go ahead and check self-intersection just so we can see what kind of intersections we have. In this case, we have the valve, and the ball of the valve actually runs right into the pipe, and they're co-located faces. So you can see here they're right next to each other. And so this is where we get pierced faces. So in this particular case, you could go through and you could stitch these edges together here and here, and you could actually extract this internal volume through manual manipulation. However, it's much easier to just go ahead and surface wrap internally in here. It will blow up a balloon inside. So you always want to be looking for topological problems with your surface to determine whether or not you want to wrap it or whether or not you want to clean it up. Okay. So I've now established I need to surface wrap. I'm going to go ahead and select Meshing Models. I'm going to wrap the surface. I'm going to hand that clean closed surface to the remeasure. And let's fill it up with polyhedral cells. Let's put some prism layers on it. And we can extend the outlet. So after I've told it how I want to mesh, now I have to tell it how big I want to mesh. That brings up a very good question. How do I pick my base size? What I would normally do is grab my measure tool and measure the distance between 2 points. So we can see here that this is a very, very large valve, or we have a scaling issue. Which brings up a very good point. If you ever notice that your geometry is not scaled correctly, you can simply go back up to the parts, grab both, transform, scale, and let's scale this by 0.01. Apply, close. I'll reset my camera with an R on the keyboard. So now, if we go back to measure, we should see this is somewhere in the neighborhood of 7, 8 millimeters. So I'm going to use a base size of about that. Use 7 millimeters. I can just type mm to get my unit. It doesn't really matter whether or not I project to CAD in this particular case, because I have a tessellated surface to begin with. These are what we call leaf level parts. So they are simply a tessellated surface like an STL file or a DBS file, which I have imported here. So when you have actual analytical CAD, Parasolid, Step, IGES, any one of the native CADs, it will be able to project onto the analytical surface. The other thing I'm going to do is I'm going to change my prism layer thickness down to, let's say, 20% of my base. So it'll be just over 1 millimeter. Okay. So I'll define my inlet as an inlet, and let's do mass flow, and my outlet as a pressure outlet. But like I said, I want to extend my outlet. So let's go and expand the geometry, and you'll see here that I have an extrusion type. I'll do a constant rate normal, and let's go 10 layers in 70 millimeters. So if you can imagine, I had my base size at 7 millimeters. So this should give me roughly isotropic cell sizing. Okay, so that is the setup of the meshing for this particular case. Let's go ahead and send it through the remesher. Okay, let's see what the mesh looks like. So, the surface wrapper has extracted a volume that is different than what I expected. What you can see here is the surface wrapper has actually extracted the largest internal volume it found, and it just so happens that the valve geometry, the housing, occupies a larger volume than the internal flow. So what we need to be able to do is specify differently how we're extracting the internal volume here. We can simply do that by going down to Mesh Conditions, change my volume of interest from largest internal to seed point. Add a new seed point, display my point tool, and I want this somewhere in the middle of my flow domain, and it looks like it is. Create and close. I'll send it right back through the wrapper. So now the wrapper has extracted the internal surface, the surface that I expected. And I'll continue on and just generate a volume mesh. So now that my volume mesh is complete, I'll change my representation so I can look at the volume mesh. And we'll see here we have roughly isotropic sizing, an extruded outlet, and polyhedrals everywhere with prism layers near the wall. Okay, so now that we've set up the meshing side, we need to go and move on to the physics side. I'm going to select models under Physics 1, and we'll do a steady state case. Let's do a liquid, segregated flow, constant density, turbulent, and let's use K epsilon solver. Let's use a mass flow rate of, say, 0.1 kilograms. So, I have now set my physics conditions. I've set my boundary conditions. Let's do a little bit of post-processing so we can keep track of some detailed pieces in this geometry. Let's go ahead and create a new scalar scene. Now I'm going to look at all the surfaces. Let's look at pressure on these surfaces. And then let's create another geometry scene where we're looking at not the volume mesh, but the initial surface, so we can actually see our valve. I'm going to delete my outline displayer here. I don't really need to look at it. And I'm going to change my opacity of my geometry displayer so I can see right through it. So let's look down the end of this. And I'm going to create a new plane section cutting right through the center of the valve. And I'll add it to a scalar displayer. So you can see here I've cut through the volume now. Alright, and then let's look at velocity. So, in addition to being able to create visual reporting, we also need to be able to create numerical reporting. So let's create a new area average value of pressure on the upstream side. So we'll call this P drop, because I know that the pressure on the outlet is specified as 0 gauge. So any pressure that's on the inlet will be basically my pressure drop. Add in my inlet boundary. I'll create a new monitor and plot from the report. Then I'm going to drag my plot into my scene. So that way I can see the pressure drop. Okay, and we're ready to go. So I'll go ahead and hit run. Okay, now that my pressure drop is pretty much leveled off, let's change our valve position. And all I need to do is go back up to my valve, transform, rotate. Let's go negative 45. Actually, we'll go 45 more. About the Z axis of our custom coordinate system. Hit apply, close. We'll volume mesh